Hello and welcome to SGN Tech Forum. Today we are going to talk about eBPF as a technology, and we'll understand how this technology, which has its roots in server side, making a big impact in cloud native networking and even in enterprise networking. The agenda for today is first we are going to understand what is eBPF and its different component, and then we'll move to Isovalent website, which is a Cisco company, and we will do a hands-on lab provided by Isovalent. Let me quickly give you a snippet of that. So we are going to perform this lab, and why Isovalent? Because it is pretty comprehensive and it saves a lot of time to build this lab locally. Why not use something which is readily available to you, to me, and understand what is this eBPF technology and feel confident about it. So let's go back to our original documentation, which is eBPF documentation, and you can see this is eBPF.io. So first understand what is the relation of eBPF.io with this technology. eBPF.io is an open source. It's an open community. Everybody can participate and share where you want to read a first introduction to eBPF. And then once you are ready to use the implementation, you can go to the respective projects. And I'll show you what are those respective projects. But let's first understand what is eBPF. eBPF, as it mentioned here, is a technology with origin in Linux kernel. It can run sandbox program in privileged context, such as operating system kernel. What is the requirement or how did it happen, basically? So you can imagine anything which is need to change Linux kernel or source code of your Linux kernel, that is a long drawn process. That means if you have a Linux operating system with certain version of kernel and then you want to modify it, is community need to vet this, someone need to validate this, and then it get committed. So it's a long run process. On the other hand, you can also use something called kernel modules. However, building these kernel modules and loading this in original source code, most of the time it requires a reboot of the operating system. And rebooting the production server may not be feasible all the time. That's why we have this eBPF, which emerge as programs that can be attached to either user space or kernel space, and it doesn't require any kind of reboot. And it also doesn't require any kind of community vetting and merging in the operating system. So that's where the eBPF originated. That's the kind of like a reason for invention. And since then, it has evolved a lot. Now you can see it has use cases in networking, it has use cases in security and observability and tracing. And we'll talk about these things in a moment. You can see eBPF has this bee like mascot for their project. And this eBPF stand for Extended Berkeley Packet Filter. You can see we have eBPF programs or trace points at user space, and we have eBPF trace points at kernel space. And here are some of the use cases. So you can do monitoring, profiling, tracing at user space versus if you attach these programs at kernel level, you can do much more. You can do security control, you can do networking, network security, load balancing, behavioral security, a lot of things because it gives you very system call level, granular level visibility. So that's the most appealing use case of eBPF. Now let's understand the hook points. eBPF programs are event driven and run when the kernel or application, depends where you are attaching, passes a certain hook points. Predefined hook points include system calls, function entry, kernel trace point, network event, and several other. And I'll show you a picture which talks about all these hook points or trace points. That will make things clear. So basically, you can take a trace point level hook and attach it between your process and scheduler so that you have the full visibility. So you can attach your filters anywhere in the operating system. And now let's understand how eBPF programs are written. So in a lot of scenarios, eBPF is not directly available. It is actually consumed by project like Cilium, BCC, BPFtrace. So these are the projects that provide an abstraction on top of eBPF and do not require writing program directly, but instead offer an ability to specify intent-based definition, which are then implemented with eBPF. So Cilium has their own set of development or trace point. BCCS has their own set of trace point, and same for BPFtrace. We are going to focus on BCC. Cilium is very popular in cloud native networking, that is the microservice based networking. The loader and verification architecture. One of the main beauty of eBPF program is once you write the eBPF program, before it get attached to Linux kernel space, there is some sort of validation. It makes sure that attaching this hook point to your operating system is not going to crash that operating system. So the fail safe mechanism is inbuilt, and that is a part of loader and verification architecture. So here you can see the verification steps ensure that eBPF program is safe to run. Because we don't have that community vetting, so we need this kind of assurance that attaching a eBPF program is not going to crash my operating system. It validates that program meets several conditions. For example, the process loading eBPF hold the required capabilities. That means it has the right privileges. The program does not crash or harm system, and so on. Also, it follows a method of JIT, just in time compilation, translate the generic bytecode of the program into machine specific instruction set. And then comes the map. eBPF map, as we say, it stores and retrieve data while you are attaching your trace point. So you think of it as like a maps as a temporary storage. And how you can store? You can store in various ways: hash tables or arrays, ring buffer, space stack, and so on. And then we have helper calls, and I'll let you read the rest of the things here. And as I mentioned, why eBPF? Because it's evolving like anything. It has implications with web technologies, cloud native technologies, and even in enterprise networking like Cisco, iOS, Nexus OS, etc. With that, what we can do, we can just look at the development tool chain. And as I mentioned, you don't develop the eBPF directly, but the development happens alongside the project, which provide an abstraction. And there are three main projects today. BCC is a framework that enable user to write Python-like programs for eBPF. And then we have BPFtrace, and it's high-level tracing language for eBPF, and available semi-recent Linux kernel. One of the main thing is BPFtrace is available in semi-recent 4.x versus BCC. It is available for newer kernels like 5.x. And then we have the BPF Go library written in Go language. We have libpf, that is in C or C++ languages. All right. So with that, I'm going to show you the BCC IOVisor project. This is a GitHub project. Search for IOVisor and then BCC. Here, I want to show you, this is a BPF compiler collection, that is a BCC project. And I want to show you a screenshot here. This is the complete Linux space, where you can see our application, runtime, system libraries, system call interface, and then file system, volume manager, so on. And these are the hook points or trace point that you can attach to those application or kernel spaces. And these are some of the pre-written eBPF trace hook that is available today under BCC library. So there is a lot of tools or functions available here already at your disposal. You can simply install the library and start using these trace point by attaching it to your networking OS or server side of the space. Now this is a right time to move into the demo or the lab. And for that, I'm going to go to playinstruct.com, and this lab is available at Isovalent website. The link is in description. You can go ahead, sign up, create an account for yourself, and then you'll be presented with this lab.